Here we go with 9.5 day 1. We're skipping over 9.4. In 9.5 we do start to shift away from sequences and series, and we'll get into some counting principles and probability in the last two sections, but today in 9.5 things get pretty specific that we're just going to look at the binomial theorem. Okay, and on the next slide I'll take you through exactly what that is. All right, so an expression that could be labeled as a binomial is anything that you're taking where you're adding two terms and then you're raising it to a power. Okay, that's the stuff that this theorem kind of applies to. Okay, I'm just going to use as the two terms to start with as x plus y, but that could change depending on the particular problem that you're doing, but we wouldn't really see that till day 2. Okay, now this one's pretty simple because anything to the 0 power is 1, so it really doesn't matter what x and y, it really doesn't matter what those terms are. What if we had x plus y to the first? Well, then that expression would just expand to x plus y. Here's a case that we've seen quite a few times. You would probably look at that and say, yeah, we'd go the route of foiling it, like write it out as x plus y times x plus y, and then, multiply or FOIL that. I'm not going to write all that out because I really just want you to see the result is it would be that. Okay? Now I keep raising the power, and this is kind of what the binomial is after. So here, if I didn't give you anything else in terms of how to do this, you might write out as x plus y times x plus y times x plus y. Or you could go back to the line before, after we had FOILed x plus y squared, and you'd say, okay, that we need to take x squared plus 2xy plus y squared and multiply it by x plus y. It'd be a lot of distributing. And it doesn't take very long because we're only at the third power. And this process of just basically using the distributive property gets really, really long, really tedious, and there's possibilities to make mistakes all over the place. This is kind of what the binomial theorem gets into, that there is a pretty quick way to get to this. And that's just a third. But you can do that pretty quickly and pretty efficiently using the binomial theorem. But that's essentially what it does, is how do you take an expression that looks like that, okay, basically this, x plus y to the n power, okay? I actually don't want to write that there. I'll just put it right over here. How to do that relatively quickly and efficiently. So now what I'm going to show you here in the next couple of slides is really the details of how the numbers work when you're doing a binomial. That part you're not going to like so much. As I'm going through this, trust that the process that I'm going to give you by the time we're done with the 2 days, you'll like. Okay, it's a pretty slick way to go about things. So here's basically the patterns that you end up with. Okay, so we would be our goal, and that's really the only kind of problems we're going to see, is to expand an expression like that. The very first term always looks like that. Okay, so x, the term that was first, starts at the n power, and y starts at 0. That would just be 1, so you effectively wouldn't see it. The first coefficient ends up being n, and here's where things get a little crazy. Not really, but a little. Is the x starts to decrease in power, and the y starts to go up. The x will decrease in power, and the y starts to go up. Now that'll continue as many times as needed, depending on how big n is. But here's all this combination stuff. We've got to introduce this new variable r, because we don't know exactly where we're at. But the coefficient is now n choose r, okay, depending on how many times we've decreased the power of x. Okay? Whatever that is, that would be the power of y. All the way to here, where we're back to n. At this point, x is all the way down to the first power. Y is almost all the way up to n. Remember, the power of y as we go through keeps getting bigger. And then we get to our last term, where x is going to be all the way down to the 0 power, and y is now going to be all the way up to n. Okay, if you look at any one of the 4 that I wrote out, it does follow this pattern. Okay, it does follow that pattern. What I want to take you through now is just a handful of examples of how would we find those coefficients. All right, so here's how these work. This would be the number in front of the x and the y. Okay, what we would call our coefficients. So this is saying, like, if n was 8, that would be this number right here, and r was 2. Okay, so once I had decreased that power 2 times. Another great way to think about that second number is that would be the power of y. Okay, once we get to the point where that second number is going up to the second. Because again, x decreases in power the whole time, y goes up. So just following that formula that was up above, that you would have 6 factorial times 2 factorial. And so we would go 8 times 7 times 6. 2 factorial is just 2. We've seen these before when we were earlier on when we just played around with factorials. That it's all about getting stuff to cancel with the bottom and the top. And that comes out to be 28. Here's 10 choose 3. What's actually going on here with the numbers is this is how many ways, if you had 10 items, how many ways that you could select 3 of them is what's happening. We'll get into that more later on. Okay? You've probably seen combinations at some point. I'm going to stop at 7, and there's 6, so that'll cancel, that'll cancel. This would be 720 on the top over 6 on the bottom. And that'll be 120. Now, just to kind of make sense of this formula sum, here's one where we should be able to predict the answer. 7 choose 0. There really should be one way to do that, right? If you have 7 items, there should be one way to choose none of them, and that would be don't select any. So this should come out to be 1. Remember, our definition of a factorial said that 0 factorial is 1. Anything divided by itself is 1. 8, choose 8. This should also be 1. How many ways are there to select 8 objects from 8? Should be 1, which would be to take all of them. So if I put in N and R, it would really look like that. And then there's R. And basically the same thing happens here, that 0 factorial is 1. And again, you get 1. I've got 4 more here because I want you to start to notice something. And it shouldn't be to any surprise here that with these coefficients, there's a pattern. Okay, there's a really, really strong pattern going on, and I want you to start to see that. So this would be 7 factorial over 4 factorial times 3. So we'd have 7 times 6 times 5 times 4. That'll cancel with that 4 factorial. 3 factorial is 6, so we have those and those that'll cancel, and 7 times 5 is 35. Now watch what happens here. Okay, notice I'm now switching over to 4. Okay, here R was 3, here was 4. 3 plus 4 is 7. There's another 6, and basically the numbers just switch spots. But how about that? It's also 35. Okay, so I mean, this would be a case where you're looking at coefficients if n was 7. Okay, and this would be your value for r, or if the power of y was 3. So now looking down here, I basically have these two cases where I only need to do one of them, because I can tell those second two numbers add up to 12, so the answer is going to be the same. (12 factorial over 11 factorial times 1 factorial. Those cancel. 12 over 1 factorial is just 12. And based on that, that one's going to be 12. You could certainly check it with the numbers, but it'll end up being 12. All right, lots of nitty-gritty details with the coefficients. Okay, you might be wondering, if we were to expand binomials, am I expecting you to do that every time? No, I'm not. I expect that you could be asked to do that on one of them, but not if you're going to actually totally expand a binomial. But here's how the deal works. We can form what's called Pascal's triangle, which is a lovely little triangle that has all these patterns that arise. Okay? So n, that's the power that you're raising it to. If that is 0, then your binomial is going to simplify to 1. It's an incredibly simple case. Okay? This pattern, by the way, is for all the coefficients. Okay? It's just for all the coefficients. What about if n is 2? Okay? The first and the last coefficients will always be 1. The middle coefficient would be 2, which if you go up to the row before, that came from 1 plus 1. Okay? Now back on the first slide, you have an example where n was 2, and notice that the coefficients were 1, 2, 1. Let's look at 3. Okay. The first and the last will be 1. 1 plus 2 is 3. See how I put the 3 in between those? Once we go up to the third power, our expanded expression will have 4 terms. And the coefficients will be 1, 3, 3, 1. Again, there's an example on the very first slide where n is 3. Notice that those are the 4 coefficients. Okay? Let's go to 4. Start and end with 1. Second coefficient would be 4. Third would be, whoops. Third would be 6. Fourth one, 4. 1, 6, 4, 4, 1, right? These numbers, we could have gotten these doing like the combinations that we were doing on the previous 2 slides. This triangle is a really, really quick way to get the pattern. Let's look at 5. 6 terms total. We'll start and end with 1. And then we're going 5, 10, 10, and 5. I'm going to do a couple more rows here. If you see the pattern, you probably could pause and see if you could finish off a couple more rows. 1, 6, 15, 20, 15, and 6. Now we're basically getting this triangle as far as we need to go because, you know, we're up to a case now where if the power of our binomial was 7, that's getting pretty high. So this triangle is pretty thorough and gives us the coefficients for most of the cases that we would see. Notice on all these two where the coefficient of the second term matches n. In this case, that's 7. 21, 35, 35, 21, and 7. Oh, let's do one more, and then we'll shut it down at 8. 1, 8, 28, 56, 70, 56, 28, and 8. And that has all the coefficients for every term if our binomial was to the power of 8. So now the one piece I'd worry about right here, and it's the very last thing we'll talk about today, is you might be looking at this and the previous 2 slides, and I know you'll like the triangle way better than doing the combinations that we did in the previous 2. Okay? And that's fine. To get the coefficients, if you were like expanding a binomial like we'll do in the second day, I'm expecting that you would do this. You really should. Okay? But I don't want you to lose sight of the connection that here's what was going on. This number right here, that's 8 choose 0. That's 8 choose 1. That 28, you could get that 28 from 8 choose 2. There's 8 choose 3. There's 8 choose 4. And remember now the pattern that we saw, that these coefficients start to repeat. Here's 8. There's 8 choose 5. Notice 8 choose 5 is the same as 8 choose 3. 8 choose 6 is the same as 8 choose 2. 8 choose 7, same as 8 choose 1, and there's 8 choose 8. Okay, so those last two slides, I was going through like kind of the non-pattern way of just mathematically how you get those coefficients. The triangle finds them a lot easier by just establishing the pattern that they follow.